freshwater demand of hydrogen production technology and their energy, like their freshwater requirement to produce hydrogen. And then I'm going to talk about the like a global freshwater reserves, present status and the projection. And then I'm going to cover about how we can integrate desalination technology and the desalination technology roles in electrolysis process. And then I'm going to talk about the case study, what I have done over here and published in a peer-reviewed journal. So if I talk about the global hydrogen demand, so the basically is global hydrogen demand is rapidly growing, and in the 2020 it was 90 million metric ton, and in the 2023 it was basically recorded as 97 million metric ton, and expected to reach up to 660 million metric ton by 2050. And as of now, most of the current demand comes from the industry. And in the upcoming years, we can see over here in this figure number 1, the demand is going to be also incurred from the refinery and the power sector. Basically is the power sector. So like hydrogen demand is going to be occur in the hydrogen sector, power sector. The reason behind it, because if we have extra renewable energy and we can store this energy in the form of hydrogen without losing its energy content. If we are going to store that excess energy in the form excess energy which we are generating from the renewable energy in battery or in any another form, so over the period of time this is going to be degrade. So after a period, like just imagine after 2 years, then the what use energy conserved at the first year, you are going to less almost like suppose you will get 90% at the end, or the like 80% at the end, or you can say the like 95% at the end. But if you are going to save that excess energy in the form of hydrogen, then the whatever amount of you are going to save at the beginning, you will get exactly the same amount of at the end. So that's why industry is moving, storing excess renewable energy in renewable energy system in the form of hydrogen. So as of now, we have 4 different kind of process to produce hydrogen, just like coal gasification and the natural gas steam reforming and the biomass and the oil gas and the water electrolysis. As of now, only 4% of the hydrogen is produced through the water electrolysis system. So due to major portion of the hydrogen was produced through the steam methane reformation or the coal gasification system. So the carbon emission through the fossil fuel based hydrogen production has reached a new milestone, that is 920 million tons in the 2023. That was like almost 1.5% higher than the 2022. And it is and these hydrogen production process, or if I say specifically, the fossil fuel based hydrogen production processes are contributing in towards the global CO2 emission, and that is almost 2.5% in global CO2 emission. So if we talk about the like how much water has been consumed by the different energy hydrogen production technology. So if you look at this figure number 3, and the natural gas, if we talk about the natural gas steam reforming, this process consumed in between 5.85 to 13.2. It depends on the quality of the water. What is the quality of the water we are supplying to the gas steam reforming process? Similarly, for the coal gasification is 9 to 11 liter per kg of hydrogen production. Similarly, for the biogasification is the same, 9 to 11 liter per kg of hydrogen production. If we talk about the specifically now the water electrolysis, it depends on the like what quality and the what electrolysis process we are using. If we are using the PEM, then it sometimes it's like 9 liter, and sometimes it's like 13 liter, sometimes it's like 70 liter as well. It depends on the manufacturer, which manufacturer is building or the manufacturing that electrolyzer system, and also what quality of water we are supplying to the electrolysis process. In this whole presentation, I'm going to talk about the focus on the water electrolysis system. So as of now, in this figure, I am just demonstrating the amount of water we need to just produce hydrogen per kg of hydrogen from the this amount of water. And there is another freshwater requirement for the different hydrogen production process, just for the cooling or pre-treatment processes, and there are the different requirements. So if we talk about the like take an example of the gas steam reforming process, like it consumes almost 21 liter of water for the evaporating cooling, and that it's also included in the hydrogen production process. If we add these the cooling water requirement as well as the water required for the hydrogen production, then it needs almost 26.85 liter of water to produce 1 kg of hydrogen production. So if we talk about, like, if we say that like cooling alone can represent around the 70 to 80% of the total water requirement in the natural gas stream reforming process. And if it's similarly, if we talk about the like hydrogen production through the electrolysis, the like it requires 9 liter of the ultra pure water plus 35 liter of the for the cooling of the electrolyzer. It's amounts equal to like 44 liter per kg. What does it mean by the like ultra pure water? The ultra pure means like it needs to be like a better than AS, or the like better or the equivalent to the quality of the ASTM grade 1. And if we are going to produce wholesome amount of hydrogen by through the electrolysis process, then the amount of water is going to be like increased by the year and year on. So in the 2023, the water requirement was measured at the 1.58 BCM, like a billion cubic meter, to the and it will grow till that 6.57 billion cubic meter to produce whole amount of hydrogen. That is our expected, like at the end of 2050, our expected hydrogen is somewhere like 660 million metric ton. So to produce that amount of hydrogen through the water electrolysis process, we need almost 6.57 billion cubic meter of water to produce that water, that hydrogen. So if we talk about the global freshwater scenario as of now, so in the current status, the like in the India subcontinent and the like other nations like India and the nearby the like Afghanistan, not is nearby the like Russian, it's in the street. They are under the high freshwater scarcity region. If we talk about the like Australia, where I am right now, so that they are in the under low water freshwater scarcity, because the like Australia has lots of freshwater reserves, less number of people over here. So that's why Australia is in a safe zone as of now. But India has a high freshwater scarcity as of now. But in the upcoming, like after like 20 to 30 years later, like this scenario is going to be like completely changed. As you can see in this graph figure number 6, the Baguio is like there's one scientist who reviewed the like freshwater status in the almost 180 nations and forecasted 87 nations will face scarcity, and that is going to be like extreme scarcity, and this will cover India, Australia, USA, China, major economies. These are, and they are going to be suffer with the fresh water, because the population is growing. Because of the population is growing, food demand is growing, water is demand is increasing, industry is utilizing lots of fresh water reserves, and they are not concerned about how we are going to refill our freshwater reserves. And there is a recent study has been conducted by a few another researchers. They reviewed the satellite data, and they found that that's a very interesting fact. They found that the regions, those were have previously lots of freshwater reserves, now they have like they gone almost 1/3 wiped out from that place, 1/3 of that, and they are getting drier faster than the getting wetter in comparison of through the rains and other method as well. And if now, so we have to think about, if we are planning to produce hydrogen through the electrolysis process, then we have to think about how we are going to meet the hydrogen freshwater demand for the hydrogen production. So there we have different kind of non-conventional freshwater reserves we can utilize, as also we know the like seawater, brackish water, or municipal water, like household water, like we are wasting, we are not refining it. And then municipal wastewater and the brackish water you can conserve it, and the household water we can store in one place, and then we can purify it and we can resupply it, and the industrial wastewater as well. But my main area is concerned towards the like seawater electrolysis. As we also know, there is in the market right now, it's very famous, the direct seawater electrolysis. But the direct sea electrolysis is a very good process, but there are several challenges with it because of the composition of the seawater. Seawater has the like huge amount of iron within itself, like and the component and the element within itself. If we talk about like the composition, then the seawater has a chlorine, sodium, sulfate, magnesium, calcium, boric acid, fluoride, and cyanide on the left side. And because of the chlorine and the bromide, it's hindered like hydrogen evaluation reaction, and they corrode electrocatalyst and undergo the competitive reaction with the chlorine evaluation reaction against the oxygen evaluation reaction. So its oxygen evolution reaction is also known as the OER. And there is another reaction that is known as the HER, that is basically known as hydrogen evolution reaction. So our main target was the hydrogen evolution reaction as most as possible. But due to the presence of the chloride and the bromide, that competition increases because chlorine easily react with the water, and this became chlorine evolution reaction started and taking over the oxygen or oxygen evolution reaction. And there is another elements available, that's a calcium and the magnesium cannot be filtered completely from the, and it's from precipitation that causes the like say OH2 formation and MgOH2 formation, and that again blocks the hydrogen evolution reactions. And when the hydrogen evolution reaction get blocked, then the hydrogen generation is less, though the efficiency of this direct seawater is become it reduces over a period of time. And there is another issue with the like direct seawater electrolysis is the biofueling because of the seawater composition, and that's again it's corrode electrode, and it's again it damages membrane, certain equipment lifespan as well due to the high current alternating to the local pH nearby the electrode. And if you have to utilize about like non conventional resources, then there is a desalination technology comes in a picture. We the like a lot of countries are already using desalination to supply fresh water to the community to meet their daily basis freshwater demand, as well as some industry are using the desalination technology to meet their demand as well. So these are the commercialized desalination technology as of now. There is, we can categorize in two different method. First, you can say the like thermal method, and the second was like a membrane method. The like in thermal method, there is like MSF, VCD, and the MED. The like MSF and the MED are very famous methods. Like MSF is like a multi-stage flash, and where is the MED is like a multi MED is like a multi-effect distillation system. And if we talk about the like RO, like everyone understood heard about it like RO system, because every single person, most of the people have their RO system at their home, like RO and the forward osmosis and the electrodialysis. But they are the commercialized one, and they are easy to integrate. And but the issue with the MSF and the MED, we need a very large area to install it and to produce water, and they required a large amount of energy, and they also need a high temperature to produce the fresh water. And whereas the RO system and the FO and the ED, they're like challenges with them. They need electricity supply to run the RO system, and we for the RO system we need a high pressure pump, and also the like RO cannot purify the saline water when it has like high salinity within itself. So that's a challenge with the RO. If there is a salinity is less than 10 gram per liter, then the RO system is good. It's easy to install. We can produce a large amount of fresh water, but still the quality of the produced water in the RO is not going to be equivalent to the ASTM first grade what we need in the electrolyzer to produce hydrogen with a minimum freshwater demand for the hydrogen production. So then how we are going to integrate the desalination technology with the electrolyzer? So basically, I'm not working in any of these technology. There is another technology that is known as the membrane distillation. That is not a commercialized desalination technology. I'm going to talk about that technology in the next slides. But before we I go into the next slides, let's talk about how can we integrate this desalination technology with the electrolyzer so we can meet the freshwater demand of the electrolyzer without any putting any burden on the freshwater reserves. So we can integrate these desalination technology, any kind of renewable energy sources like with the ocean energy, solar energy, hydropower, or the wind energy, or the geothermal energy, or the thermal energy. We can use any of these energy and we can run these system. And to integrate this one, I have shown this figure in the figure number 9, desalination technology integration with the electrolyzer. Basically, we are going to first treat the water. The water is coming in, is the saline water is going in, and where we are going to treat this water and then purify it. Then we are going to supply it to the electrolysis technology, and we are going to produce hydrogen and the oxygen, and we are going to store it. But the challenge with this desalination technology, it come up with the handling their brine, because when we are going to produce fresh water, then how we are going to handle the rest of the water, like that known as the brine, because that brine is going to be like a very high saline water. So this is the biggest challenge when we talk about the large scale terms. But for this thing, we have so many other processes we can integrate over here. So the like a mineral extraction process we can add over here. So we can extract the minerals from the highly saline water, or we can add another desalination technology over here. So we can again purify this highly saline water, or you can say the brine water. And in that way, in the system, in that way we can meet the freshwater demand of the electrolyzer. And but if we want to reduce the freshwater demand of the electrolysis, then we can do one more thing. If we can add over here a ion exchange purification unit in between the water treatment technology and the electrolysis technology, to improve the quality of the produced water from the water treatment technology. So now let's discuss about the like membrane distillation technology. So this technology is not commercialized yet, but like scientists are working on developing a large scale system, because it's easy to operate and easy to install. Because it need only two plates. Two plates means of like a one on the top side, another is the bottom side. In between there is a membrane. You can supply water from saline water from the one side and the cold water from the another side, and the due to temperature difference on the feed side and the permeate side, the fresh water is going to be transferred from the feed side and the permeate side. So let's discuss about the like what is the membrane desalination technology basically means. In the membrane desalination technology, basically fresh water is produced due to temperature difference that creates a pressure difference in a feed side and the permeate side, and due to the pressure difference, the water getting transferred from the feed side to the permeate side, and that fresh water is collected by the different technology, different methods. And because of the way of collection of the fresh water on the permeate side, that's categorized the membrane desalination technology. So membrane desalination technology basically has four different types. One is a DCMD, SGMD, VMD, and the AGMD. So they are basically categorized based on the collection of the water on the permeate side, because it has like membrane desalination technology has the two sides, feed side and permeate side, and both our sides are separated by a membrane in between. In the feed side, hot saline water is supplied, and the permeate side are the cold fresh water. That's pure water, not just like a fresh water. That's pure fresh water, or you can say like a DI water, deionized water we supplied. And when the like due to high temperature on the DCMD feed side, the temperature difference created a pressure difference on the feed side to the permeate side. Feed side has a higher pressure and the permeate side has a lower pressure due to low temperature. And the fresh water started getting transferred from this through this membrane and get condensed on the permeate side. And this water goes to the water storage tank, and this process keeps going on until we finish all the heated saline water. And because of this is a direct contact with that feed water to the permeate side, it is known as the DCMD. And this is a sweep gas membrane distillation system. In the sweep gas, basically we use a gas to collect the water on the feed on the permeate side, and this water is get condensed on the condenser in here. And in the case of the VMD, that is known as the vacuum membrane distillation system. Instead of using a water on the permeate side or the gases on the permeate side, we just install a condenser along with the vacuum pump, and we just extract the water through it, and then the water is get condensed in the condenser. And similarly for the AGMD, that's the air gap membrane distillation system. This air gap membrane distillation system has like a similar functioning like the SGMD. In the air gap membrane distillation system, there is a one extra chamber generally installed. That is like this is a feed side chamber. This is a membrane. On the permeate side, this is another air gap chamber. And then we have another chamber, that is the permeate side freshwater supply chamber. So when the freshwater supply over here, then due to the cold temperature here, on this side of the plate is the temperature is less. On the feed side, temperature is high. Due to temperature difference, the pressure difference created, and the freshwater is transferred through this membrane from feed side to the permeate side. And in that way, freshwater get produced, and it can be collected over here in the flux. As a terms of flux, we generally use terms flux in the membrane desalination technology. And at the low temperature, DCMD has a higher flux production in comparison with all other desalination technology. But when it's operating at the high operating temperature, like more than 70 degrees Celsius, then the VMD has a higher flux production. So I have just did one case study for the King Island, that is near King nearby the Australia, in between the basically Tasmania and the Victoria, and their population is near about like 1670 in the 2020, 2020 or 2022. I didn't clearly remember as of now. I just published, and that is case study has been published in a two peer-reviewed journals. First, in the name of the like freshwater supply for the hydrogen production and underestimated challenge. If anyone is interested in detail, who can just go and check this paper. And similarly, for the second paper is towards self-water sufficient renewable hydrogen power supply system by utilizing the electrolyzer and the fuel cell waste heat. And this is the Kings Island. Basically, this is the whole Australia. This is like Victoria in here, and this is Tasmania. In between there is a Kings Island. The reason behind of selection of this site, because of the low level of rainfall in the upcoming, in previous years. So if you look at this like a historical rainfall percentile in the data of the King Island, if you look at this one at the corner over here, is shows the deficiency, and the most of the population lives in these islands or just like on the coastal areas. So that is the main reason behind the selection of this site. So this is the electricity demand of the King Island. Basically, it's a community electricity demand where we use for this electricity for their daily uses, for all of the industrial and every purpose. And most of the energy right now in King Island was met through the renewable energy sources. That is almost 65%. The rest of 35% was met through the diesel generator. So my main agenda was to remove that diesel generator and to install a hydrogen like electrolyzer and the fuel system to meet the rest of the electricity demand. So we can reduce the carbon emission through the power through the renewable energy system. So I designed, I use basically Homer Pro software and MATLAB software, including the spreadsheet, to design my whole system. And I designed 4 different kind of system. That like the first one is like wind turbine PV system included system. Another was like just like wind turbine in the PV system. There is no battery in the second term. The battery is not included in the second figure. And then the C in this one is the like wind turbine system is only is here, but like, and this fourth one is the like PV system is only here. So in the first one, I am using 2 energy storage technology, battery and the fuel cell system. In the second one, I am using the like only the fuel cell system, and the rest on the C and D, I'm using again the 2 energy storage system. What was the reason behind using 2 energy storage system rather than using 1? Because the fuel cell system needs some minimum amount of minimum energy demand. It can we cannot run fuel cell just for the meeting 1 kilowatt or the like 0.5 kilowatt of our electricity demand. We cannot use fuel cell system because it's a large size fuel cell system. So we have to make sure we can meet that small amount of energy requirement through another energy storage system. And the better thing is that installing a battery instead of using a diesel generator or another thing, because the battery is not going to emit any carbon, but there is some carbon emission is going to happen through the manufacturing of the battery. We cannot deny it. Okay, so I just rank these renewable energy system based on their levelized cost of electricity and the capacity shortage. If you look at this one, the first one is the minimum has the minimum levelized cost of electricity, that is the 0.19 and almost $0.2 per kilowatt hour. And but in this one, I added another criteria. The criteria was like most important. Another criteria was that minimum hydrogen reserve in the tank, because most of the study throughout the like journals I have found, they are considering we can go up to the 0 reserve in the hydrogen tank, but we cannot go because we are using hydrogen tank and the electrolyzer and the fuel cell system as an energy storage technology. This should be use as a battery, like similar as the concept of the battery, because we cannot drain battery 100%. Similarly, we cannot drain electrolyzer and the fuel cell system 100%. So we have to put some certain amount of restriction. We can go, we can use 80% or the 90% of the hydrogen from the hydrogen tank to meet the demand, and the rest of the demand is going to be met through the either from battery or either from wind turbine or the PV system. So the now I'm going to talk about this figure number one, because this was has the lowest levelized cost of electricity. So so throughout the year, the hydrogen produced from the system was recorded as like 69,954 kg per year, and the first one, if we add, and I selected one electrolyzer that was like it's a Siemens electrolyzer, and that basically consumes 17 liter per kg of water to produce 1 kg of hydrogen, and that 70 liter is written on their manufacturing data sheet. So I am using their data, and then I just assume if this freshwater requirement can be reduced to the 9 liter freshwater requirement to produce 1 kg of hydrogen, then the how much freshwater we need to meet the freshwater demand of this electrolyzer. So as in the system, the electrolyzer operates annually for the 4,579 hours and produces 69,954. So based on the 17 liter freshwater requirement to produce 1 kg, it needs almost 1189 meter cube per years fresh water. And if that electrolyzer consumes somewhere like 9 liter of fresh water, then it needs almost half of that, not exactly half, but almost half of that, 629.59 meter cube per year. So my target was to understand how much waste heat was generated through the electrolyzer and the fuel cell during this operation, and can I recover this waste heat to energize any of the desalination process. So I can desalinate a seawater and supply that water to the electrolyzer to overcome the burden on the freshwater reserves to meet the electrolyzer demand. So then I did some manual calculation through Excel, and then I found the almost 96.5% of the waste heat from the electrolyzer can be recovered. And similarly, for almost 67% of the waste heat from the fuel cell can be recovered easily. And this is my goal was to find a suitable desalination technology which can be integrated with the electrolyzer and the fuel cell system. So my main goal was to recover waste heat at low temperature. So I assumed my electrolyzer system is operating somewhere like 65 degrees Celsius, and fuel cell system is operating at the 65 degrees Celsius, but it can also go, fuel cell system can go up to the like 100 and 120 degrees Celsius. And similarly, the electrolyzer can go up to the 100 and 120 degrees Celsius. And I was basically working on the PEM, proton exchange membrane electrolyzer, and the proton exchange membrane fuel cell system. And if someone is going to install the solid oxide gas fuel cell system or another like solid oxide electrolyzer cell, then they are going to operate at the high temperature. Then we can easily recover the waste heat from there for the desalinating seawater, and we can integrate any of the MSF and the MED technology to produce fresh water to meet the freshwater demand of the electrolyzer. So, but as in my study, I was working with the low temperature electrolyzer and the high fuel cell, so I just installed a DCMD system which has the like a high flux production capacity at low temperature, like below 70 degrees Celsius. So I selected that one. If the temperature is going above the 70 degrees Celsius, so I definitely go for the VMD, that is a vacuum membrane distillation system. So this is just like a simple schematic for the membrane distillation system. So if you look at this one, this has a two compartment. One is a like feed side compartment. This is another side is a permeate side compartment. On the feed side compartment, this feed is coming after recovering a heat from the electrolyzer or the fuel system. This feed saline or the heated saline goes through this the feed side compartment of the DCMD system, and from the permeate side of the DCMD system, the fresh water supplied. And due to the temperature difference, because of the on the left hand side or the feed side, high temperature is there. On the right hand side, where the permeate side is the low temperature is there. Due to this temperature difference and separated by this membrane, and membrane has a very low pore, like the pore size is somewhere like 0.22 micrometer. So due to this temperature difference, the pressure differences gets created, and the fresh water is collected on the surface over here, and then it get transferred through the pores on the right hand side or the permeate side. And there is no saline. Maybe over a period of times, like if our membrane desalination system is operating for like 2 months or 3 months or more than like 5 months, then maybe there is some crack we can see on the surface of this membrane. So we have to do a regular maintenance to avoid any contamination on the permeate side. And there is a three different kind of heat transfer takes place on this one. From first one takes place on the pump feed side, that is known as the convective heat transfer, feed side convective heat transfer. Another takes place with the conductive heat transfer place, that through this membrane. Membrane is actually membrane is a solid, and the thickness of membrane is somewhere like 200 micrometer. So it's a solid, we can say, like feed side, it's like a feed side convective heat transfer, then the conductive heat transfer, then again convective heat transfer. So these are the three mode of heat transfer takes place in this whole system. And this is like how the temperature polarization and the concentration polarization work over this membrane surface. So it's showing in this graph. As you can see, that when the flow is flowing through this the feed side compartment, because of the as soon as we move away from this membrane surface, that the salinity or the saline water moves very fast, and over a period of time, due to temperature difference, the salinity get condensed or the deposited over this membrane surface, and because of that, the concentration polarization happens, and then it reduces the flux production of this MDCMD system. So ours now is the main question is how much fresh water we can produce from this waste heat DCMD system in integration with the waste heat through waste heat recovery of the electrolyzer and the fuel cell system. So I just did first I did how much waste heat recovery can be done. So there is two things. We can recover almost 96% of the electrolyzer waste heat, and from fuel cell we can recover almost 67% of the waste heat. And that is the 67% of the waste heat is an effective waste heat that is available for the recovery. But generally, electrolyzer or the fuel cells generate more than that, but we cannot recover 100% of that. The reason behind it, because when we are going to start our electrolyzer or fuel cell system, then some amount of energy is going to be stored within the system body itself, because at the beginning, the system is at the low temperature, and over a period of time, it is going to be warm up and it will store some amount of energy within itself. And that amount of energy we cannot recover from the system. So I just subtracted that amount of energy, and then I calculated how much energy we can recover. And then the answer I got, that was 96.8% of the waste heat can be recovered from the electrolyzer, and the 67% of the waste heat can be recovered from the fuel cell system. So if I am saying over here it's 100%, so 100% waste heat means that is the 100% of 96.8%. The waste heat, if we can recover that 96.8% of the waste heat effectively, then we can meet almost 85% of the way, or 85% of the annual freshwater demand of the electrolyzer. Okay, and this demand is met through when we are considering 17 liter of fresh water that we require to produce 1 kg of hydrogen. If we are considering it's 9 liter of fresh water, we need to produce 1 kg of hydrogen, then this amount goes more than this one. So because this amount is almost like 11, like it's 1016 meter cube annually, and the demand was like 629.59 meter cube. That is too much. Okay. So in this figure, and this is I'm showing over here. So I have consider three freshwater demand to produce 1 kg of hydrogen. One is 17, another is 9 liter. So if we reach like here, if we are considering up to this point, so then on the upper zone, no additional freshwater requirement. On the downward this direction, we need additional freshwater to meet the hydrogen demand to produce hydrogen efficiently without touching the freshwater reserve. So now the main concern was like how, if we are going to integrate the DCMD system, then how it is going to impact the cost of the whole renewable energy system. Will it impact too much or like a small one? So I just changed the membrane area. A membrane area means like a DCMD size, direct contact membrane distillation system size. So I increased the DCMD size from 10 meters square to the 16 meters square. And then I saw then I calculated the change in the cost separately, how much capital cost is going to be changed, how the operational maintenance is going to be changed, and what is the change we are going to see in the replacement cost, and how the levelized cost of hydrogen is going to be changed. So surprisingly, the change was not that much, and the change in the cost in the other, like if you talk about the capital cost, it was like 0.24 to the 0.26. It depends on the area which we are considering. If we are considering 10 meters square of the DCMD size, then the change in the capital size is going to like 0.24, and the operational cost is going to be changed by 0.87, and the levelized cost of hydrogen is going to be like changed to 0.34 percent, not more than that. And if we increase the membrane size of DCMD system, then this to the 16 meters square, then the capital cost will change by 0.26%, and the hydrogen production cost is going to be changed by 0.37% only. That means it is feasible to integrate the DCMD system, waste, not just DCMD system, or a membrane desalination system to recover the waste heat from the electrolyzer and the fuel system to produce fresh water for the hydrogen. As you look at this one, so the levelized cost of hydrogen is, you can see here, it's a bit high, but we do not need to worry about, because the primary goal of the designed renewable hydrogen energy system was to supply energy and the fresh water to the system. So as I am producing hydrogen from the excess energy, that means it will have definitely a high hydrogen production cost. If I am planning to produce hydrogen using complete energy produced from the wind turbine or the PV system or the both, then the hydrogen production cost is going to be less, and it will come down below than $4 per kg. And then I just after doing this simulation modeling, then I just developed an experimental setup where, as you can see over here, this is there is a 3 chamber, and in the yellow sign, under the yellow sign, 1, 2, and the third. In the left hand side, this is a stack with the cooling system. The stack is representing the electrolyzer and the fuel cell system. And the right hand side of this is representing the waste heat power DCMD system. This white box, similar to the white box, this is a DCMD system. The size of this DCMD system was nearby like 0.14 meters square. It's very less. And then I had a connection with like several connections. And this is a permeate water storage tank. And this is a heat exchanger device. And there is another heat exchanger. This is a cell and tube heat exchanger. And this cell and heat exchanger basically used to recover heat from this custom design stack that is mimicking the electrolyzer and the fuel cell system. And when this is a saline water tank. First, I'm supplying this saline water through the pump, and then it passes through this saline water, cell and tube heat exchanger, where it's collect heat from the cooling water of this stack, and then it enters into the DCMD system, where due to the temperature difference in between the feed side to the permeate side, then it causes a pressure difference, and it's due to the pressure difference, the fresh water getting produced, and then it transfers from the feed side to the permeate side, and then this fresh water get transferred through this one, and it passes through this again heat exchanger, because I want to control the temperature of this permeate tank. Otherwise, what will happen, due to the heat transfer happening inside this DCMD module, because there is 3 mode of heat transfer, as I discussed before: convection, conduction, then again convection. The temperature of this permeate water is going to be increased. If you are not going to control the temperature of this permeate water, then what will happen, that the temperature on the feed side and the permeate side is going to be slowly reduce the difference between them, and then the flux production is also going to be decreased. And the main idea was designing this whole system was to analyze this system this stack performance, then how much time it is going to take to generate the heat, like effective available heat that we can recover, because we cannot supply immediately heat some water to this system, because if we supply, just like if we turn on this system, and then if we immediately start supplying cooling water, then what will happen, this water will start extracting heat before reaching this designed stack at the desired temperature. So it was necessary, we have to wait for at least 5 to 6 or 10 minutes. It depends on what is the desired temperature to operate this stack. Based on that, we have to wait, and there is a record. These are the data center where we are going to monitor the temperature profile. When the temperature reaches the desired temperature, then you are going to turn on this water supply and then you are going to split this water to the each cell. And this basically stack is made up of 5 different cells. And this is a one heating and cooling profile of the design stack. So we can analyze how much time it is taking to effective heat and how much time it's taking to produce fresh water. So basically, and when I just turned on my system, it was initially at the constant temperature, like environmental temperature. When I just turned on, it started rising, and it reached to my desired operating temperature. That was the 60 degrees Celsius. But then I found if I am supplying the cooling water of the stack at immediately when the system is reaching at the 60 degrees Celsius, then there was a premature temperature drops occurs over here. So then what I did, so I just waited for a few more minutes to reach is like a higher temperature. I did a heat and trial multiple of times to get a desired suitable temperature when because I have to achieve my desired operating temperature. So you have to do the like couple of time heat and trial and get an plot, so you can see, okay, now if that temperature will reach, then you can start supplying cooling water, and then you will get the equal amount of heat all the time without losing the temperature of the design stack. So when it reaches approximately 340 degrees Celsius, then 340 Kelvin, then I started supplying water, and then it's the temperature of that stack will drop, and then it will reach somewhere like 333.5. It will not reach 33 below 333, but it will reach at 33.5 something, near about something, over a period of time. And if I zoom this one, so it looks something like this. So in between from the like 57 to the like almost 115, in between this time it reaches to the it stabilizes. After this, the temperature of the stack is getting stabilized, and then the cooling water which taking heat, that means it's taking effectively heat from the stack. And when I just stopped heating the stack and stop the cooling water, then I let the system design stack cool down naturally to see how much time it is going to take to come to the environmental temperature of the, because this is important, because when we are going to use electrolyzer and the fuel cell system as an energy storage technology in any renewable energy system, and we are also recovering waste heat, so it's important to see what is the heating and cooling profile of electrolyzer and the fuel cell, because if it is and because of this heat profile, you can calculate how much heat is going to be stored within the electrolyzer and the fuel system, which you cannot recover. So this is a very important to plot this system heating and cooling profile. So in this case, when I was just running my system at the 60 degrees Celsius, so plates in the middle achieved stack operating temperature in almost 450 minutes, and while the end planes means like this, like which was just nearby the stack, the like supporting plate, they reached the temperature 60 degrees Celsius 7.25 minutes. And when the end plate or the like reach 60 degrees Celsius, then the middle plates, the temperature increases to this temperature. So to ensure the stability and prevent the drop below the desired operating temperature, the cooling water was supplied to the plate in the middle in the 5.15 minutes. Similarly, the cooling water supplied 8.25 minutes, regulate the temperature steady state. And then I noticed after the heating and the started, this figure is showing the flux production and the mass of the fresh water with the time. And when I started heating the stack over here, this was at the beginning, up to 15 minutes, there was no flux production occurs. After 15 minutes, they slowly started producing flux. It started producing flux, but after like almost 45 minutes, it gets stabilized, and also you can say like it started increasing and getting stabilized, and but after like 1 minute, it's become completely stabilized. So not 1 minute, it's 1 hour. It's completely stabilized, and the freshwater production was noted as 0.81 kg per meter square at 45 minutes. And this can be this upward trend continues as a substantial heated further enhance the system, the thermal performance, and yielding flux values up to 1.02 kg per meter square hours at 60 minutes and 1.16 kg per meter square hour at 75 minutes. And this is the maximum flux production I recorded when I was supplying 300 watt of heat to the stack. So the amount of heat supplied to the stack was completely fixed. So the main another point was how much salinity was in the produced fresh water. Then I varied the salinity in the saline water. Then I recorded the salinity in the produced water was in between 3 to 5.5. It was not too much. And similarly, I measured the conductivity because the performance of the electrolysis depends on the conductivity of the fresh water. So it also increases from the like 7.567 micro Siemens per centimeter to the 13.81 micro Siemens per centimeter at 291.15 Kelvin, when the conductivity of the feed element increases from the 25 micro Siemens per centimeter to the 88.2 micro Siemens per centimeter at 293.15 Kelvin. So thank you for patiently listening me. Now I'm going to just show that like which software I use to design my renewable energy system first. And that software was basically Homo Pro, and then I integrated with the MATLAB. Then I used a spreadsheet, or there is another software you can use, that's a Transys. I also work on the Transys, but basically I work on this one since the beginning, so I was presenting out that one. Please let me know if you can see my screen for this one.
No, I think it is not visible. The software screen.
Yes, yes, yes.
No, it is not visible. Actually, your presentation is visible.
Okay, just give me one second. Is it visible now? Is it
Yes,
visible?
yes, yes.
Okay, thank you. Thank you. So this is a Homer Pro software, and as you can see over here, so this is basically has several components, like you can see loads, component, resources, projects, and help. So first, what you need to do, you need to go through here. So first you have to select the electricity demand, and you have to find, is there any a peak month like January, July, or any? No. So you can select none, and then you have to select what kind of energy profile you are going to give. It's a residential, commercial, industry, community, or blank. Black means you are going to assume you don't know what is the electricity profile is for what. So you are going to select uh, blank over here, or if you know the that electricity demands is basically related to the residential or the commercial, or then you can select one of them, and then you have to click over here, import and edit that file, and then you have to click and okay, then you will see the like profile. So I'm going to just for an example, I'm going to choose like residential, then I'm going to click okay, and I'm selecting no peak month, so it's okay. So when I'm going to select this one, so you are going to see the another screen that's this is showing the electrical load of throughout the electrical load of the resident throughout the year. And as you can see over here, this is the average kilowatt hour per day, average kilowatt, peak, load factor. So what type of load is that? Is it AC or is it a DC? Or then you can scale this whole electricity demand by any number. You can change this number by putting over here. You can say it's like 12 kilowatt or 15, 20, whatever is that. It's up to you if you want to do that. And this is and there here is the source like a random variability. It's a day-to-day variable. Does it mean by the day-to-day variable? It shows the like electricity demand, how electricity demand is changing day to day. So like it's this software is getting from the data, it's 10% change in the electricity demand. And similarly, what is the time step? Time step means like hourly. How what is the frequent change in hourly? So it's 20% is change. So it automatically is getting from this data. It's not assuming from their side. It's from getting from this data. And then based on that, you have to jump on the component where you are going to select. You are planning to what kind of system you are planning to design. Then you can select on the PV system. If you want to plan to like PV system, you can select. There is a different kind of catalog. You can go and select any PV system from here. Let's suppose I'm just generating flat PV, then I'm going to add it. Then you have to put like a capital cost replacement and other one. Here you can see Homer optimization search. You can fix the size of that PV system. And in the left hand side, you can see this is the PV system is going to produce DC power and your demand is in AC. So you need a converter. So you need to install one converter that is going to collect this power to the demand. And then you have to add like GHI, that's a global, this is the solar irradiation. You have to give the solar because you need to produce electricity. through the PV panel. So first you are going to select here, and this is the resources downloaded. And how I'm getting, because first you have to identify your location from this map. You have to select anywhere in the map, and then you will get your location for which location you want to design your PV system. Now you have designed your system, but it says considering adding a battery, because sun is not available 24. So we have to consider one battery. So I'm going to add battery energy storage system, or you can add anything, any another energy storage system. Like you can add here, you can add any boiler, electrolyzer, or fuel cell, anything you can add. And then you have to just go and run your calculate, and it will start calculating the system automatically. And then this is the best system he founds. And then if you go to the tables, you can find multiple options over here, like overall, like this was the category. This is the best system this software is finding, and this is the overall. You can see there is a plenty of combinations of this arrangement. You can pick any of that based on your requirement, or you can click any of them. You will get like all the detail, like cost summary, cash flow, compare economics, electrical, renewable penetration, generic, anything. You will get it from here. Based on that, you can design your system. And this was the software demonstration. Thank you for your patiently listening me. I'm coming back to my presentation. If anyone have any doubt, please let me know. Thank you, guys. Thank you, everyone.
Yeah. Thank you so much, Mr. Pranjal from RMIT University. He was showing such a very insightful presentation on desalination, which is actually the major problem nowadays, and we would be facing a lot of problem in near future. And yes, a lot of work is also going on at the same time to mitigate the upcoming effects. And you have shown really such a wonderful presentation on it. And also, because time is not permitting, my voice is not coming, I think.
It's coming, it's coming.
Okay. Someone has commented. Okay. So you have also shown the software with which can simulate or you can get the results. Yes, it was really very nice, and time is not permitting us. But in future, in our other FDPs, we will try to have you on the session with this software. And I request the participants, if you are having any questions, you may ask Mr. Pranjal Kumar.
Or if anyone have if want to more information, you can email me, or you can we can hang out, like we can chat later on. Or if you have any
Yes.
question now, you can.
Yes. Thank you. As I said, I can see in the chat box, everyone is praising you. And yes, thank you so much,
Thank you.
Mr. Pranjal, for joining us. And we will look to have you on other sessions also. Thank you so much again.
Thank you, Dr. Aman. Thank you, Dr. Prasad.
Thank you, Pranjal. Thank you, Pranjal.
Yeah, thank you.
Okay, so here was the Mr. Pranjal Kumar from RMIT, that is the Royal Melbourne Institute of Technology, Australia. And the next session we are having from Dr. Prerna Nasine. And before she is joining, we can wait for 2 minutes so that she will be joining. And after 2 minutes at 10:32, we will be having our next session.